We're not standing still in space. We are falling through an enormous cosmic hollow, a region where matter is significantly thinner than the universe expects it to be, and we have been falling through it for billions of years without knowing. This is not speculation or theoretical physics divorced from observation. This is measurement. In 2013, three astronomers named Ryan Keenan, Amy Barger, and Lennox Cowie published a paper that quietly confirmed something unsettling about our position in the cosmos. They had been counting galaxies across vast distances, mapping the distribution of matter in every direction we can see, and what they found was a consistent deficit. No matter which way they looked, out to distances of roughly 1 billion light-years, there were fewer galaxies than cosmological models predicted there should be. Not by a small margin. Not by an amount that could be dismissed as statistical noise or observational error. The deficit was approximately 20%. 1/5 of the matter that should surround us, according to the standard model of cosmology, simply was not there. The pattern was not random. It was not localized to one region of sky. It was spherical, centered on us, extending outward in all directions to a scale so large that it dwarfs every familiar structure we know. The Milky Way, our local group of galaxies, the Virgo cluster, even the Laniakea supercluster to which we belong, all of these exist within this underdense bubble, this absence, this hollow in the fabric of cosmic structure. They called it the KBC void, named after the initials of the three astronomers who confirmed its existence. Though the structure itself is far older than its discovery, older than humanity, older than Earth, as old as the observable universe itself. The KBC void is not empty. Space is never truly empty. Even the darkest regions between galaxies contain gas, dark matter, radiation, the faint glow of starlight scattered across billions of years. But the void is sparse in a way that defies the expectations built into our cosmological models. It is underdense. The matter that does exist within it is spread thinner than average. Galaxies separated by greater gulfs than they should be, clusters fewer and farther between. The scale of this underdensity is what makes it remarkable. The void extends roughly 1 billion light-years in every direction from our position, making it approximately 2 billion light-years across, though the boundaries are not sharp, not walls but gradients where density slowly rises as you move outward toward the denser regions that surround it. To give this a sense of scale, the distance from Earth to the Andromeda Galaxy, our nearest large galactic neighbor, is about 2.5 million light-years. The distance across the local group, the small cluster of galaxies to which the Milky Way belongs, is roughly 10 million light-years. The Virgo cluster, a large collection of galaxies that exerts gravitational influence over our local group, lies about 50 million light-years away. The Laniakea supercluster, a structure so vast it was only mapped in detail in 2014, spans some 500 million light-years. The KBC void is larger than all of this. It is a structure on a scale that approaches the size of the observable universe's largest features, and we are inside it, have always been inside it, embedded deep within its underdense interior. The discovery was not entirely without precedent. Astronomers have known about cosmic voids for decades. In the 1970s and 80s, as surveys of galaxy positions began to map the three-dimensional structure of the universe, it became clear that galaxies are not randomly distributed. They cluster. They gather along filaments and sheets, forming a vast cosmic web. And between these filaments lie voids, vast bubbles of relative emptiness where few galaxies form. These voids are a natural consequence of cosmic structure formation. In the early universe, tiny fluctuations in density, imprinted during the first moments after the Big Bang, grew over time under the influence of gravity. Regions that were slightly denser than average attracted more matter, growing denser still, eventually collapsing into galaxies and clusters. Regions that were slightly less dense than average lost matter to their surroundings, becoming voids, expanding as matter drained away toward denser regions. This process is well understood, well modeled, and well observed. Voids are a standard feature of the cosmic web. They occupy the majority of space. Roughly 90% of the volume of the universe is void, with matter concentrated into the remaining 10%, gathered along filaments and nodes like dew condensing on a spiderweb. But the KBC void is different. It is not different in kind, but in degree. It is larger and deeper than simulations of cosmic structure formation typically produce. When cosmologists run computer simulations of how the universe should evolve from the initial conditions set by the Big Bang, starting from the tiny fluctuations we observe in the cosmic microwave background and letting gravity shape structure over billions of years, they do produce voids, but voids of this scale, with this depth of underdensity, are rare. Not impossible, but statistically improbable. Finding ourselves inside such a structure is unexpected under the assumptions that underlie the standard model of cosmology. The standard model is called lambda cold dark matter, often abbreviated as lambda CDM, and it is the most successful framework we have for understanding the large-scale structure and evolution of the universe. It is built on a few key components. Lambda refers to the cosmological constant, a term Einstein introduced into his equations of general relativity and later called his greatest blunder, but which has been revived in modern cosmology to represent dark energy, a mysterious form of energy that permeates all of space and drives the accelerated expansion of the universe. Cold dark matter refers to a hypothetical form of matter that does not emit, absorb, or reflect light, that interacts only through gravity, and that moves slowly compared to the speed of light. This dark matter is believed to make up roughly 85% of all matter in the universe, far outweighing ordinary matter, the protons, neutrons, and electrons that make up stars, planets, and people. The model also includes ordinary matter, radiation, and the rules of general relativity that govern how matter and energy curve spacetime, and how that curvature dictates the motion of matter and energy. The lambda CDM model is extraordinarily successful. It explains the cosmic microwave background, the faint glow of radiation left over from the Big Bang, with exquisite precision. It explains the large-scale distribution of galaxies, the way they cluster and form filaments. It explains the abundances of light elements like hydrogen and helium formed in the first minutes after the Big Bang. It explains the accelerated expansion of the universe discovered in the late 1990s. It is the standard model for good reason. But the KBC void sits uncomfortably within this framework. Its size and depth are at the tail end of the statistical distribution predicted by lambda CDM. Not forbidden, but unlikely. And if the universe is statistically homogeneous, if our location is not special, then finding ourselves in such an unusual structure should itself be unlikely. This touches on a foundational assumption of modern cosmology, a principle that has guided the field for nearly a century. It is called the cosmological principle, and it states that on sufficiently large scales, the universe is homogeneous and isotropic. Homogeneous means it looks the same everywhere. Isotropic means it looks the same in every direction. The principle does not claim that the universe is uniform on small scales. Obviously, it is not. There are stars, planets, galaxies, voids, clusters, immense variation in density from place to place. But averaged over scales of hundreds of millions or billions of light years, the principle asserts these variations should smooth out, and the universe should look statistically the same no matter where you are or which way you look. This principle is not arbitrary. It is motivated by both philosophical considerations and observational evidence. Philosophically, it is a statement of mediocrity, an assertion that we do not occupy a special location in the cosmos. Observationally, it is supported by the cosmic microwave background, which is remarkably uniform across the sky, varying in temperature by only about 1 part in 100,000. This uniformity suggests that the universe, at the time the microwave background was emitted some 13 billion years ago, was remarkably smooth, and the lambda CDM model builds on this smooth beginning to explain how structure grew over time. But the cosmological principle is an assumption, not a law of nature, and the discovery of the KBC void raises the question of whether this assumption holds as precisely as we have believed, or whether it is approximate, valid on average, but violated in detail, and whether violations of sufficient scale might affect our measurements in ways we have not fully accounted for. The implications of living inside a large void extend beyond questions of cosmic geography. They affect measurement. They affect what we see and how we interpret it. This is because voids are not static. They are dynamic structures, shaped by gravity, and gravity behaves differently inside a void than it does in regions of average density. To understand why, consider how gravity works. Mass curves space-time, and this curvature dictates how objects move. In a region of high density, where matter is abundant, gravity pulls inward, attracting more matter, deepening the gravitational well. In a region of low density, where matter is sparse, there is less gravitational pull from the interior and more from the surrounding denser regions. The net effect is that matter inside a void experiences an outward pull, a gentle acceleration toward the boundaries where density is higher. This is not an explosion. It is not matter being pushed by pressure or repelled by some force. It is simply the geometry of gravity. If you're in a valley surrounded by mountains, gravity pulls you toward the mountains, not because the valley repels you, but because there is more mass in the mountains and less beneath your feet. Similarly, a galaxy inside a void is pulled toward the denser regions that surround the void, not because the void repels it, but because there is more mass outside than inside. This outward acceleration has a consequence. It means that voids expand, not at the same rate as the average expansion of the universe, but faster. The galaxies that mark the boundaries of a void move apart more quickly than the galaxies in denser regions. And as they do, the void grows, becoming larger and emptier over time. This expansion is not hypothetical. It has been measured. Astronomers have tracked the motions of galaxies in and around voids and found that they are indeed receding from the void centers faster than the average cosmic expansion would predict. These motions are called peculiar velocities, a term that means motion relative to the smooth expansion of space itself. The universe is expanding, carrying galaxies apart, and this expansion is described by the Hubble law, which states that the recessional velocity of a galaxy is proportional to its distance. But galaxies also move through space due to local gravitational influences, the pull of nearby matter, or the outward acceleration from underdense regions, and these motions add to or subtract from the smooth Hubble flow. In dense regions, galaxies are pulled inward toward clusters, giving them peculiar velocities directed toward the centers of those clusters. In voids, galaxies are accelerated outward, giving them peculiar velocities directed away from the void center. These peculiar velocities are typically hundreds of kilometers per second, sometimes more, and they're superimposed on the much larger velocities due to cosmic expansion. For nearby galaxies, where the expansion velocity is relatively small, peculiar velocities can be a significant fraction of the total motion, and this matters when we try to measure the expansion rate of the universe itself. The expansion rate is quantified by a number called the Hubble constant, usually denoted h, and it is one of the most important numbers in cosmology. It tells us how fast the universe is expanding today, and it sets the scale for cosmic distances and the age of the universe. For decades, measuring the Hubble constant has been a central goal of observational cosmology, and for decades, the measurements have improved in precision. But in recent years, a problem has emerged. Two different methods for measuring the Hubble constant, both of which are precise and carefully calibrated, give answers that disagree. The disagreement is not small. It is not within the margins of error. It is a 9% difference, and both methods have been checked and rechecked, refined and re-refined, and the discrepancy remains. This is known as the Hubble tension, and it is one of the most significant unsolved problems in cosmology today. One method measures the expansion rate of the early universe by analyzing the cosmic microwave background, the faint glow of radiation from the Big Bang. The patterns of temperature fluctuations in this radiation encode information about the contents and expansion history of the universe, and by fitting these patterns to the predictions of the Lambda CDM model, cosmologists can infer the value of the Hubble constant. This method gives a value of approximately 67 kilometers per second per megaparsec. The other method measures the expansion rate of the nearby universe by observing galaxies and standard candles, objects whose intrinsic brightness is known, allowing their distance to be calculated from their apparent brightness. The most common standard candles for this purpose are Type Ia supernovae, exploding stars whose peak brightness is remarkably uniform, and Cepheid variable stars, pulsating stars whose period of pulsation is related to their luminosity. By measuring distances to galaxies and their recessional velocities, astronomers can directly calculate the Hubble constant. This method gives a value of approximately 73 kilometers per second per megaparsec. Both numbers are stated with small error bars, typically a few percent or less, and the errors do not overlap. This means that at least one of the measurements is wrong, or more troubling, that both could be correct, but measuring different things, which would imply that the universe is not expanding uniformly, that the expansion rate differs between the early universe and the nearby universe, and that something about our models or our understanding is incomplete. Various explanations have been proposed. Perhaps there is new physics in the early universe, some additional component or interaction not included in the lambda CDM model that affects the microwave background. Perhaps there are systematic errors in the distance ladder, the chain of calibrations used to measure distances to distant galaxies. Perhaps dark energy is not a constant, but evolves over time, changing the expansion rate in ways not captured by the standard model. Or perhaps we live in a large underdense region, a void, and the local expansion rate we measure is not representative of the universe as a whole. This last possibility is the one that the KBC void brings into sharp focus. If we are inside a large void, and if that void is expanding faster than the average cosmic expansion, then the galaxies we observe nearby, the ones we use to measure the Hubble constant through supernovae and Cepheids, may have peculiar velocities that bias our measurement upward, making the local expansion rate appear faster than it truly is on average. The logic is straightforward. When we measure the Hubble constant using nearby galaxies, we are measuring their recessional velocities and distances. The velocity comes from the redshift of their light, the stretching of wavelengths caused by the expansion of space as light travels from the galaxy to us. The distance comes from standard candles or other distance indicators. The Hubble constant is simply the ratio of velocity to distance. But the measured velocity includes both the smooth Hubble flow and any peculiar velocity due to local gravitational effects. If the galaxies we are measuring are inside or near a large void, and if they are being accelerated outward by the void's gravitational structure, then their velocities will be higher than the smooth Hubble flow alone would predict. We would interpret this extra velocity as part of the cosmic expansion, inferring a higher Hubble constant than is actually characteristic of the universe as a whole. The size of this effect depends on how large and how deep the void is, and on how far out we measure before the sample becomes dominated by galaxies outside the void where the bias diminishes. For the KBC void, calculations suggest that the effect could be several percent, potentially enough to explain part or all of the Hubble tension. This is not a fringe idea. It has been explored in peer-reviewed papers, and while it is not universally accepted and remains debated, it is a viable explanation that fits the observations without requiring exotic new physics or modifications to general relativity. But accepting this explanation requires accepting that we live in an unusual place, a place where the local structure of the universe is not representative of the whole. And this is precisely what the cosmological principle tells us should not be the case. If the universe is homogeneous on large scales, then our local measurements should reflect the global average, and we should not need to account for local peculiarities. The existence of the KBC void suggests that homogeneity, while a useful approximation, may not hold as precisely as we would like, at least not on the scales where we make our most important measurements. This is philosophically uncomfortable. For centuries, the history of astronomy has been a history of displacement, of learning that we are not at the center, not special, not privileged in our perspective. Copernicus displaced Earth from the center of the solar system. Hubble displaced the Milky Way from any privileged position in the universe, showing that galaxies extend in all directions as far as we can see and that the universe is expanding uniformly. The cosmological principle is the culmination of this process, the assertion that not only is there no center, no edge, but that the view from any location is statistically the same. To suggest that we happen to live in a large void, a statistically unusual structure, feels like a step backward, a return to the idea that our location matters, that our measurements might be biased by where we happen to be. And yet, the observations suggest this might be the case. The galaxy counts show an underdensity. The Hubble tension persists. The void is not a hypothesis. It is a measurement. Understanding the physics of voids requires understanding the interplay between gravity and cosmic expansion, and this interplay is subtle. In the standard cosmological framework, space itself is expanding, carrying galaxies apart, and this expansion is described by the scale factor, a mathematical function that quantifies how much space has stretched since some reference time. In the early universe, the scale factor was small, and the universe was denser and hotter. As time passes, the scale factor increases, space expands, and the universe cools and thins. The rate at which the scale factor changes is governed by the contents of the universe, by how much matter, radiation, and dark energy it contains, and by the equations of general relativity. In a perfectly uniform universe, one in which matter is distributed exactly evenly, the expansion would be perfectly smooth and uniform, and every point in space would recede from every other point at a rate proportional to the distance between them. But the universe is not perfectly uniform. It is clumpy with variations in density, and these variations create local gravitational fields that affect how matter moves. In dense regions, gravity slows the expansion, and in extreme cases, it can halt the expansion entirely and cause matter to collapse into bound structures like galaxies and clusters. In underdense regions, gravity accelerates the expansion, causing voids to expand faster than the average. This might seem counterintuitive at first. We're used to thinking of gravity as attractive, as pulling things together. So how can it cause acceleration away from a low-density region? The answer lies in the relative nature of gravitational effects. Gravity does not push. It always pulls. But in a void, there is less matter inside pulling inward than there is matter outside pulling outward, and the net effect is an outward acceleration. Imagine you are standing on the inner surface of a hollow spherical shell of mass. According to Newton's shell theorem, a result that also holds in general relativity for spherically symmetric configurations, the gravitational field inside such a shell is zero. The mass of the shell pulls equally in all directions, and the forces cancel. Now, imagine the shell is not complete, that there's a hole in it, a region where the mass is reduced. The cancellation is no longer perfect. There's a net force toward the denser parts of the shell, away from the hole. This is analogous to what happens in a void. The void itself does not push galaxies outward, but the denser regions surrounding the void pull galaxies toward themselves, and from the perspective of someone inside the void, this appears as an outward acceleration. In the context of cosmic expansion, this acceleration is added to the overall expansion rate, making the void expand faster than average. The effect is not uniform throughout the void. It is weakest at the center, where the pull from surrounding matter is balanced in all directions, and it increases toward the edges, where the pull from the dense regions becomes more directional. Galaxies at the edge of a void on the boundary between underdense and overdense regions experience the strongest outward acceleration, and as they move outward, they carry the boundary with them, causing the void to grow. This growth is not indefinite. As the universe expands and dark energy becomes increasingly dominant, the role of matter in shaping expansion diminishes, and eventually, in the far future, dark energy will dominate so completely that local density variations will have negligible effect on expansion rates. But in the current epoch, billions of years after the Big Bang, but before the dark energy domination is complete, density variations still matter, and voids are actively expanding faster than average. The KBC void is in this phase, growing, carrying us along with it. And the peculiar velocities imparted to galaxies by this expansion are imprinted in the redshifts we measure, subtly biasing our inferences about the global expansion rate. Measuring peculiar velocities directly is challenging because they are mixed with the much larger velocities due to cosmic expansion, but it can be done through careful analysis. One approach is to measure distances using methods that do not rely on redshift, such as standard candles or the Tully-Fisher relation, which links a galaxy's rotation speed to its luminosity, and then compare these distances to the distances inferred from redshift, assuming a smooth Hubble flow. Any difference indicates a peculiar velocity. Another approach is to look for coherent flows, large-scale motions of galaxies in a particular direction, which can be evidence of gravitational attraction toward a massive structure or acceleration away from a void. Observations have detected such flows. One of the most famous is the dipole in the cosmic microwave background, a pattern in which the radiation is slightly hotter in one direction and slightly cooler in the opposite direction. This dipole is interpreted as due to the motion of our local group of galaxies through the rest frame defined by the microwave background, moving at approximately 600 kilometers per second toward a direction in the sky near the constellation Hydra. This motion is itself a peculiar velocity caused by the gravitational attraction of matter in that direction, and it indicates that the Milky Way is not at rest with respect to the average cosmic expansion. We are falling towards something, and simultaneously, we are being accelerated outward by the void in which we reside. The cosmic web, the large-scale structure of the universe, is the context in which these motions occur. The web is a three-dimensional network of filaments, walls, and nodes, with voids filling the spaces between. The filaments are elongated structures along which galaxies are strung like beads on a string. The walls are flattened sheets where filaments intersect. The nodes are dense clusters where multiple filaments converge. The voids are the empty spaces, the bubbles that make up most of the volume. This structure arises naturally from the gravitational growth of initial density fluctuations. In the early universe, fluctuations were tiny, just one part in 100,000 variations in density, imprinted by quantum fluctuations during an earlier epoch called inflation. Over billions of years, gravity amplified these fluctuations. Dense regions became denser, attracting matter from their surroundings. Underdense regions became emptier, losing matter to nearby dense regions. The process is nonlinear and complex, and the web-like structure that emerges is a generic prediction of gravitational collapse in an expanding universe. Simulations of structure formation, which start from the observed fluctuations in the cosmic microwave background and evolve them forward in time using the laws of gravity and cosmic expansion, reproduce the cosmic web with remarkable fidelity. These simulations show filaments, walls, voids, clusters, all arising from the same initial conditions and the same physical laws. The fact that simulations match observations so well is one of the great successes of the Lambda CDM model. But there is a subtlety. The match is statistical. Simulations produce a universe that looks like ours on average, with similar distributions of structure sizes and shapes, but any particular realization, any particular simulation, will differ in detail from the real universe. The positions of individual galaxies, the exact shapes of voids and filaments, these are contingent, dependent on the specific initial conditions. What matters is whether the statistics of the real universe match the statistics of simulated universes. And in most respects, they do. But the KBC void is at the edge of this statistical match. It is a rare structure, one that occurs in simulations, but not often, and the question is whether its rarity is so extreme that it challenges the model or merely indicates that we happen to live in an unusual, but not impossible configuration. To quantify rarity, cosmologists use statistical measures of large-scale structure, comparing the observed universe to the distribution of structures in large ensembles of simulations. One such measure is the multiplicity function, which counts how many structures of a given size and density exist per unit volume. For voids, This function describes how many voids of different sizes and depths the universe should contain. The KBC void, with its size of roughly 2 billion light-years and its depth of roughly 20% under density, falls into a regime where the multiplicity function predicts that such voids are rare but not absent. Depending on the exact definitions used and the volume of the universe surveyed, finding one such void might be expected or might be somewhat surprising, but is not a clear violation of the Lambda-CDM model. However, this statistical assessment assumes that we are randomly placed within the universe. If we are not randomly placed, if there is some selection effect that makes observers more likely to arise in certain environments, then the statistics change. This is an application of the anthropic principle, the idea that our existence as observers places constraints on the properties of the universe we observe. For example, if intelligent life requires a certain density of matter to form galaxies, stars, and planets, but also benefits from living in a region where the expansion rate is conducive to structure formation, then observers might be more likely to find themselves in environments that are neither too dense nor too empty. And the probability of finding ourselves in a large void might be higher than the naive probability based on volume alone. These arguments are speculative and difficult to quantify, and many physicists are uncomfortable with anthropic reasoning, but they remain a logical possibility when assessing the significance of our location. The cosmic microwave background provides a complementary way to study voids and their effects. The microwave background is a snapshot of the universe, as it was about 380,000 years after the Big Bang, when the universe cooled enough for electrons and protons to combine into neutral hydrogen, allowing light to travel freely through space for the first time. This light has been traveling ever since, stretched by the expansion of the universe from visible light in a microwave radiation, and it carries information about the conditions in the early universe. The temperature of this radiation is remarkably uniform, about 2.725 Kelvin in every direction, but there are tiny fluctuations, hotter and cooler spots, that vary by about 1 part in 100,000. These fluctuations correspond to the density variations in the early universe that would later grow into galaxies and large-scale structure. The pattern of fluctuations can be analyzed statistically, and the results are encoded in the power spectrum, a function that describes how much fluctuation there is on different angular scales. The power spectrum of the microwave background fits the predictions of the Lambda-CDM model exquisitely well, and this is one of the model's greatest triumphs. But the microwave background also interacts with structures that formed later, along the line of sight from the surface of last scattering to us, and these interactions can leave subtle imprints on the radiation that provide information about large-scale structure, including voids. One such effect is called the integrated Sachs-Wolfe effect, named after the physicist who first described it. When microwave background photons travel through a region of space with a time-varying gravitational potential, they gain or lose energy. If the potential is becoming deeper, photons lose energy, appearing cooler. If the potential is becoming shallower, photons gain energy, appearing hotter. In a static universe, these energy changes would cancel out as photons enter and leave a gravitational well. But in an expanding universe, the potential changes with time, and the cancellation is not perfect. In regions where matter is collapsing and forming structures, the potential deepens, and photons lose energy. In regions where voids are expanding and dark energy is becoming dominant, the potential shallows and photons gain energy. The result is that microwave background photons passing through expanding voids are slightly heated, and regions of the sky that correspond to lines of sight through voids should appear slightly warmer than average. Conversely, photons passing through collapsing overdense regions should appear slightly cooler. This effect has been measured by cross-correlating maps of large-scale structure, which identify the locations of voids and overdense regions. With maps of the cosmic microwave background, astronomers have detected the integrated Sachs-Wolfe effect, confirming that the expansion and gravitational evolution of structure does indeed leave an imprint on the microwave background. The signal is faint, only a few microkelvin in amplitude, but it is statistically significant and consistent with the predictions of the Lambda CDM model. For the KBC void, the integrated Sachs-Wolf effect would create a subtle warming of the microwave background in the direction of the void, but the effect is weak and spread over a large angular scale, making it difficult to isolate from other sources of temperature variation. Nonetheless, the existence of the effect is another piece of evidence that voids are real, dynamic structures that influence the universe around them. Another observable signature of voids is found in the large-scale distribution of galaxies itself through a feature called baryon acoustic oscillations. In the early universe, before the formation of the cosmic microwave background, the universe was a hot, dense plasma of photons, electrons, protons, and dark matter. The photons and ordinary matter, the baryons, were tightly coupled by electromagnetic forces, forming a fluid that could support pressure waves, sound waves traveling through the plasma. Density fluctuations in this fluid would propagate as acoustic waves, moving outward from their points of origin at a speed determined by the pressure and density of the plasma. These waves continued until the moment of recombination, when electrons and protons combined into neutral atoms, decoupling the photons from the baryons and ending the pressure support. At that moment, the sound waves stopped, frozen in place, and their final extent set a characteristic scale, roughly 500 million light-years in the present-day universe, called the sound horizon. This scale is imprinted in the distribution of matter. Regions that were dense at recombination, surrounded by shells of matter pushed outward by acoustic waves, became preferred sites for galaxy formation, and the result is a subtle excess in the number of galaxy pairs separated by the sound horizon distance. This excess is the baryon acoustic oscillation signal, and it can be measured by analyzing the clustering of galaxies as a function of separation. The sound horizon acts as a standard ruler, a known physical scale that can be used to measure distances and the expansion history of the universe. Observations of baryon acoustic oscillations in galaxy surveys agree well with the predictions of the Lambda CDM model and provide an independent measurement of the Hubble constant and other cosmological parameters. But like other measurements, baryon acoustic oscillations can be affected by peculiar velocities. If galaxies are streaming toward or away from structures due to gravitational infall or void expansion, their positions in redshift space, the space defined by measuring distances from redshifts, will be distorted compared to their positions in real space. These distortions, called redshift space distortions, can be measured and used to infer the large-scale velocity field, providing yet another probe of structure and another way to test whether we live in an underdense region. The evidence for the KBC void comes from multiple independent measurements and analyses, each with its own strengths and limitations. The original discovery by Keenan, Barger, and Cowie was based on counting galaxies in a survey called the Super Cosmos Sky Survey, a catalog of objects detected on photographic plates taken by telescopes over several decades. They counted galaxies as a function of distance, estimated from redshifts, and found a consistent deficit out to distances of about 1 billion light-years. Subsequent studies using different surveys and different methods have largely confirmed the underdensity, though there is some debate about the exact size and depth of the void. Some studies find a shallower underdensity extending over a larger region. Others find a deeper underdensity in a smaller region. These differences arise from the challenges of measuring large-scale structure, from uncertainties in galaxy distances, from variations in how the void is defined, and from the fact that voids do not have sharp boundaries. A void is not a sphere with a well-defined edge. It is a complex, irregular region where density gradually decreases toward the center and gradually rises toward the edges. The exact contours depend on the scale being probed and the density threshold used to define underdensity. Despite these uncertainties, the broad conclusion remains robust. There is an underdense region centered on our position, extending to scales of roughly 1 billion light-years, and this underdensity is large enough and deep enough to have measurable effects on our observations. If we accept that we live in a large void, The next question is whether this affects our understanding of the universe in ways beyond the Hubble tension. One area where it might matter is in our measurement of the matter density of the universe, often denoted by the symbol omega. This parameter quantifies what fraction of the universe's energy density is in the form of matter, both ordinary and dark, as opposed to dark energy. The matter density affects the growth rate of structure, the clustering of galaxies, the abundance of galaxy clusters, and the behavior of gravitational lensing. It is measured through a variety of techniques, and like the Hubble constant, different methods sometimes give results that are not in perfect agreement. If we live in an underdense region, our local measurements of structure, the number of clusters, the degree of clustering might be biased low, leading us to infer a lower matter density than is actually characteristic of the universe as a whole. Similarly, measurements that rely on the distribution of galaxies within a certain volume might be biased if that volume is not representative. Some studies have explored whether the KBC void could resolve tensions in measurements of the matter density, and the results are mixed. The effect is smaller than the effect on the Hubble constant, but it is not negligible, and it is another reminder that our local environment might bias our inferences about global properties. Another area where the void might matter is in tests of general relativity and alternative theories of gravity. General relativity has been tested extensively in the solar system, in binary pulsar systems, and more recently through the detection of gravitational waves from merging black holes and neutron stars. It has passed every test with remarkable precision. But these tests probe gravity in regimes of relatively strong fields and small scales, scales where gravity is well understood. On cosmological scales, on the scales of galaxies, clusters, and the universe as a whole, gravity is tested primarily through its effects on the expansion of the universe and the growth of structure. These tests also support general relativity, but the evidence is less direct and less precise than in the solar system, and there is more room for alternative theories to fit the data. One motivation for considering alternatives is the dark matter problem. The fact that galaxies and clusters seem to contain far more mass than can be accounted for by visible matter suggests either that there is an unseen form of matter or that gravity behaves differently on galactic scales than general relativity predicts. Most cosmologists favor the dark matter explanation, but a minority have pursued modified gravity theories. One of the oldest and most studied is modified Newtonian dynamics, or MOND, proposed by physicist Mordechai Milgrom in the 1980s. MOND modifies the law of gravity in the regime of very low acceleration, which corresponds to the outskirts of galaxies, and it can explain galaxy rotation curves without invoking dark matter. However, MOND struggles to explain the behavior of galaxy clusters, the cosmic microwave background, and large-scale structure, and is not widely accepted. But there are relativistic versions of MOND and other modified gravity theories that attempt to address these shortcomings, and some of these theories predict that the formation of large-scale structure, including voids, might differ from the predictions of general relativity with dark matter. In some modified gravity theories, the growth of structure is faster than in general relativity, leading to deeper voids and denser clusters forming earlier in cosmic history. If this were the case, the existence of a large, deep void like the KBC void might be more natural in a modified gravity framework than the standard lambda-CDM framework. This has motivated some researchers to explore whether the void could be evidence for modified gravity. The challenge is that modified gravity theories must also explain all the other successes of general relativity and lambda-CDM, from the cosmic microwave background to gravitational waves, and most modifications that enhance structure formation tend to conflict with observations in other areas. For example, some modified gravity theories predict a different expansion history than lambda-CDM, which would affect the distances to supernovae and the age of the universe. Others predict gravitational waves that travel at different speeds than light, which is ruled out by observations of neutron star mergers where both gravitational waves and light were detected and arrived nearly simultaneously. As a result, while modified gravity remains an active area of research, the standard model with dark matter and dark energy remains the best fit to the full suite of observations. The KBC void, as unusual as it is, does not by itself require new physics. It can be explained within the Standard Model as a rare but allowed statistical fluctuation. But rarity brings with it a discomfort, a sense that something remains unexplained. If the void is so rare that only a few such structures should exist in the observable universe, and if we happen to live in one of them, does that not suggest that either we are extraordinarily lucky, or that our models are missing something, or that there is a selection effect we have not properly accounted for? This is a version of the fine-tuning problem that appears in other areas of cosmology and physics. The universe has many properties that seem to be finely tuned for the existence of complexity and life. The density of dark energy is small, but not zero, and if it were much larger, structures like galaxies would not have formed. The density of matter is within a narrow range that allows for both structure formation and a universe that lasts long enough for stars to form and evolve. The strengths of the fundamental forces are such that atoms can exist and chemistry can occur. Any of these properties, if significantly different, would result in a universe inhospitable to life as we know it. One response to this fine-tuning is the anthropic principle, the argument that we can only observe a universe compatible with our existence, and therefore we should not be surprised to find ourselves in a universe with properties conducive to life, even if such a universe is rare among all possible universes. Another response is the multiverse hypothesis, the idea that there are many universes, each with different properties, and we live in one of the rare ones that allows for observers. The KBC void might be seen through a similar lens. If voids of this size are rare but not forbidden, and if being in a void has no particular advantage or disadvantage for the formation of life, then finding ourselves in one is a matter of chance, and no explanation beyond probability is needed. But if being in a void does affect habitability, perhaps by altering the rate of galaxy collisions, the intensity of cosmic radiation, or the availability of heavy elements, then the anthropic principle might suggest that observers are more likely to find themselves in such environments, and the apparent rarity would be explained by selection bias. These arguments remain speculative and are difficult to test, but they illustrate the philosophical depths to which the question of our cosmic location can lead. The cosmological principle was meant to sidestep these questions by asserting that location does not matter, that the universe is the same everywhere and we are not special. The discovery of the KBC void challenges this assertion, not by refuting it outright, but by introducing ambiguity. The universe may be homogeneous on average, on scales larger than the void, but on the scales where we make our measurements, where we test our theories and infer the properties of the cosmos, there is structure, and that structure affects what we see. We cannot step outside our location and view the universe from elsewhere. We are embedded in it, and our measurements are inextricably tied to where we are. This does not mean that cosmology is hopeless, that we cannot learn about the universe from our vantage point, but it does mean that we must be careful about extrapolating from local measurements to global conclusions, and we must account for the possibility that our local environment introduces biases we have not fully quantified. The age of a universe is another quantity that could be affected by the Hubble tension and by our location in a void. The age is inversely related to the Hubble constant. A faster expansion rate implies a younger universe, because less time has passed since the Big Bang when the expansion began. With the Hubble constant measured for the cosmic microwave background, the inferred age of the universe is approximately 13.8 billion years, with an uncertainty of only a few tens of millions of years. With the Hubble constant measured from supernovae and Cepheids, the inferred age is closer to 12.7 billion years, over a billion years younger. This difference is significant because there are independent constraints on the age of the universe from the ages of the oldest stars. Globular clusters, dense collections of hundreds of thousands of stars that orbit the Milky Way and other galaxies, contain some of the oldest stars in the universe. By measuring the brightness and temperature of stars in these clusters and comparing them to models of stellar evolution, astronomers can estimate the ages of the stars, and the oldest globular clusters appear to be around 13 billion years old, perhaps older. White dwarf stars, The remnants of low-mass stars that have exhausted their nuclear fuel also provide age estimates. White dwarfs cool over time, and the coolest, dimmest white dwarfs are the oldest. The coolest white dwarfs observed suggest ages consistent with 13 billion years or more. These age estimates are consistent with the microwave background measurement of the Hubble constant and the corresponding age of the universe, but they are in tension with the faster expansion rate measured locally. If the universe is only 12.7 billion years old, then the oldest stars will be nearly as old as the universe itself, leaving little time for the first generation of stars to form, evolve, and produce the heavy elements that later stars require. This would be problematic and is another reason why the Hubble tension is taken seriously. If the resolution to the Hubble tension is that we live in a void and the local expansion rate is higher than the global average, then the age problem is resolved. The true Hubble constant would be the lower value inferred from the microwave background. The universe would be around 13.8 billion years old, and there would be ample time for the oldest stars to form. The higher local value would be a consequence of our location, not a reflection of the true global expansion rate. This resolution is attractive because it solves two problems at once, the Hubble tension and the age tension, without requiring new physics. But it requires accepting that the cosmological principle is violated to a degree that affects precision measurements, and this remains a point of contention in the community. Some cosmologists are comfortable with this idea, viewing the principle as a useful approximation but not a strict law. Others are more resistant, preferring to seek explanations that preserve homogeneity and isotropy as closely as possible. The debate is ongoing, and it will likely only be settled by future observations that probe the expansion rate and large-scale structure with greater precision and over larger volumes of space. Looking to the future, the role of dark energy and the fate of the universe become intertwined with the dynamics of voids. Dark energy, whatever it is, drives the accelerated expansion of the universe. Its density remains constant as the universe expands, while the density of matter decreases, and over time, dark energy becomes the dominant component, controlling the expansion. At present, we are in a transitional era. The universe is roughly 14 billion years old, and dark energy and matter are of comparable importance. In the past, matter dominated, and the expansion was decelerating. In the future, dark energy will dominate increasingly, and the expansion will accelerate without bound. This has profound consequences for the structure of the universe. As dark energy takes over, the regions of space that are not gravitationally bound into clusters will accelerate apart, and the voids will grow without limit. Filaments will thin and eventually break. Walls will dissolve. Clusters, which are held together by their own gravity, will survive as isolated islands in an ever-expanding sea of emptiness. Galaxies outside our local group will recede beyond the cosmic horizon, the boundary beyond which light cannot reach us because the space between us and them is expanding faster than light can travel through it. The observable universe will shrink, not in physical size, but in content. Distant galaxies will fade from view as their light is redshifted into invisibility. The cosmic microwave background will cool and dim, eventually becoming undetectable. Over trillions of years, the universe will become a vastly larger and emptier version of what we see today, with isolated clusters separated by voids that stretch for incomprehensible distances. And if intelligent observers exist in that far future, they will see a very different cosmos than we do. Those future observers, if they're confined to a single cluster, will see a sky nearly empty of galaxies. They will observe only the stars and galaxies in their own cluster, bound together by gravity, and they will see darkness beyond. If they attempt to measure the expansion of the universe, they will find that everything outside their cluster is receding so fast that it is beyond their horizon. They will have no direct evidence that the universe is larger than their cluster. They will have no access to the cosmic microwave background, which will have cooled and redshifted into invisibility. They will have no view of distant galaxies from which to measure supernovae and Cepheids. If they develop cosmology, They might infer from the dynamics of their cluster and the motion of galaxies within it that the universe is expanding, but they will not be able to measure the expansion rate or the history of the universe the way we can. They will lack the observational evidence that we have used to develop the Big Bang model, and it is conceivable that they might develop very different theories about the origin and nature of the cosmos. They might even conclude that the universe is static, eternal, and consists only of their cluster, with no knowledge of the vast structures that existed in earlier epochs and now lie beyond their reach. This is a sobering thought. It suggests that our ability to understand the universe is contingent on the epoch in which we exist and on the observational evidence available to us. We are fortunate to live in an era when the cosmic microwave background is still observable, when distant galaxies are still within our horizon, when the expansion history of the universe is still encoded in the light that reaches us. In a sense, we live in a golden age for cosmology, a brief window of time in the history of the universe when the evidence for the Big Bang and a large-scale structure is accessible. Future civilizations, or civilizations that arose earlier in cosmic history, when the universe was too young and hot for complex structure to exist, might not have this access. The idea that cosmology is contingent on epoch and location is not new, but it has taken on new relevance with the discovery of the accelerated expansion and the realization that dark energy will dominate the future. It is also relevant to our situation in the KBC void. If we live in an unusually underdense region, we are, in a sense, seeing a preview of the future. Voids are regions where dark energy already dominates over matter. The expansion within a void is driven more by dark energy than by the inertia of the Big Bang or the gravitational pull of matter. This is why voids expand faster than average. In the far future, the entire universe will be like the interior of a void, with dark energy driving expansion everywhere and matter confined to isolated bound structures. By studying the dynamics of the KBC void, we are studying what the universe will become. The void is a laboratory for understanding the effects of dark energy on expansion, structure, and observability. It is also a reminder that the universe is not static, that the structures we see today are transient, and that the cosmos is constantly evolving toward a state of increasing emptiness and isolation. The cosmic web itself is a temporary phenomenon. The filaments, walls, and nodes that define the large-scale structure of the universe today are the result of billions of years of gravitational amplification of tiny initial fluctuations, but they are not permanent. They are products of a particular epoch, the epoch when matter and dark energy are both significant. In the past, when the universe was younger and denser, structure was less pronounced. In the future, when dark energy dominates completely, structure will freeze and then dissolve as expansion accelerates. The voids are the first structures to feel this transition. They are already dominated by dark energy, already expanding without the restraint of gravitational attraction, already thinning and growing. The filaments and clusters will follow, not by dissolving into voids, but by becoming isolated, cut off from each other by the expansion of space, each becoming its own separate universe, causally disconnected from the rest. This is the ultimate fate of a universe with dark energy. It is a fate of profound loneliness, of horizons shrinking, of knowledge being lost, of civilizations, if they exist, being confined to ever smaller regions of space as the rest of the cosmos becomes inaccessible. But this fate lies trillions of years in the future. In the present, the universe is still structured, still evolving, still accessible to observation. The KBC void, for all its implications, is just one structure among many, and the universe beyond the void is rich with galaxies, clusters, and filaments extending as far as we can see. The challenge for cosmology is to disentangle the effects of local structure from the global properties of the universe, to determine which of our measurements are representative and which are biased, and to build a model that accounts for both the large-scale homogeneity assumed by the cosmological principle and the small-scale inhomogeneities that characterize the cosmic web. This is not an easy task, and it requires observations that span vast distances and probe structure on multiple scales. Current surveys, such as the Sloan Digital Sky Survey, the Dark Energy Survey, and the upcoming Vera Rubin Observatory and Euclid satellite, are mapping the positions and redshifts of hundreds of millions of galaxies, providing unprecedented views of large-scale structure. Future surveys will go deeper and wider, mapping billions of galaxies, probing the universe to distances where the effects of local structure like the KBC void become negligible, and allowing us to measure the global expansion rate and matter distribution with accuracy that is not biased by our location. These future observations will test whether the void is the explanation for the Hubble tension or whether the tension has a different origin. They will also test the cosmological principle itself, determining whether the universe is truly homogeneous on large scales or whether there are larger structures, supervoids, or superclusters that extend beyond the scales we have mapped so far. If such structures exist, they would pose a serious challenge to the Standard Model, suggesting that the scale of homogeneity is larger than we thought, or that the universe is fundamentally less uniform than the principle assumes. So far, observations have not revealed such structures. The largest surveys to date show that the universe becomes increasingly uniform as you look at larger scales, consistent with the principle, and the statistical properties of large-scale structure match the predictions of the Lambda-CDM model averaged over large volumes. But the universe is large, and our surveys, while impressive, still cover only a fraction of the observable universe. There is always the possibility that we have not yet looked far enough or in enough detail to see the full picture. The KBC void also raises questions about the nature of cosmic variance, the idea that any finite volume of the universe will contain statistical fluctuations that make it differ from the average. Cosmic variance is a fundamental limitation on what we can learn from observations confined to a single location. No matter how precise our measurements, we are always sampling just one realization of the statistical distribution of structures, and that realization may not be perfectly representative. This is analogous to trying to determine the outcome probabilities of a die by rolling it only a few times. Even if the die is fair, you might happen to roll more sixes than expected or fewer ones, and you would need many rolls to average out the fluctuations and determine the true probabilities. In cosmology, we are stuck with one roll, one universe, and we cannot observe other universes to average out the fluctuations. We can compare our observations to simulations, which generate many realizations of universes with the same statistical properties, but we cannot escape the fact that we live in a particular realization, and that realization might be unusual. The KBC void is an example of this. It is within the range of structures predicted by simulations, but it is at the tail of the distribution, and finding ourselves inside, it is a reminder that cosmic variance is real and that it limits our ability to infer global properties from local measurements. In practical terms, cosmic variance affects the precision with which we can measure certain cosmological parameters. Parameters that depend on the abundance or clustering of structures on scales comparable to the size of our survey volume are more affected by cosmic variance than parameters that depend on smaller scale phenomena. For example, the amplitude of the matter-power spectrum on large scales, which describes the degree of clustering of galaxies separated by hundreds of millions of light years, is more uncertain due to cosmic variance than the amplitude on small scales, which is averaged over many more independent structures. Similarly, measurements of the Hubble constant that rely on nearby galaxies within a few hundred million light years are more affected by local peculiar velocities and structure than measurements that use more distant galaxies or the cosmic microwave background, which averages over the entire observable universe. The KBC void, extending to roughly 1 billion light years, affects measurements on these intermediate scales, and accounting for it requires either correcting for the local density and velocity field or extending measurements to distances well beyond the void, where the bias diminishes. Some recent studies have attempted to make such corrections. By modeling the density field in our local universe, including the KBC void and the surrounding structures, and calculating the expected peculiar velocities of galaxies within this field, it is possible to subtract these peculiar velocities from the observed redshifts and obtain a more accurate measurement of the Hubble flow. These corrected measurements suggest a lower Hubble constant, closer to the value inferred for the cosmic microwave background, supporting the idea that the void is part of the explanation for the tension. But these corrections are model-dependent. They rely on assumptions about the density field, the relationship between the distribution of galaxies and the distribution of matter, and the laws of gravity that govern peculiar velocities. Different models give different corrections, and the uncertainties in the models can be comparable to the size of the effect being corrected. As a result, while the corrections are suggestive, they are not yet definitive, and more work is needed to refine the models and reduce the uncertainties. Another approach is to look for independent evidence of the void in observations that do not rely on galaxy counts. One such observation is the kinematic Sunyaev-Zel'dovich effect, a phenomenon in which the motion of galaxy clusters relative to the cosmic microwave background imprints a distinctive pattern on the radiation. When a cluster moves through the microwave background, the hot electrons in the cluster scatter photons, shifting their energies in a way that depends on the cluster's velocity. By measuring this effect for many clusters, it is possible to map the large-scale velocity field and infer the density distribution that gives rise to it. If we live in a large void, the velocity field should show a systematic outward flow from the void center, and the kinematic Sunyaev-Zel'dovich measurements should detect this. Some studies have reported hints of such a flow, but the results are not yet conclusive. The signal is weak, and the measurements are difficult, requiring large numbers of clusters and careful subtraction of other effects that can mimic the kinematic signal. Future surveys with more sensitive instruments and larger cluster samples will improve the constraints and may provide clearer evidence for or against the void. Gravitational lensing is another tool that can probe the density distribution in our local universe. When light from a distant galaxy passes through a region of space containing matter, the gravity of that matter bends the light, distorting the image of the galaxy. The amount of distortion depends on the total mass along the line of sight, including both ordinary matter and dark matter. By measuring the shapes of many distant galaxies and analyzing the statistical patterns of distortion, it is possible to map the distribution of matter between us and the galaxies. This technique, called weak gravitational lensing, has been used to map large-scale structure out to distances of billions of light-years, and it provides an independent measure of the matter density that does not rely on the distribution of galaxies. If the KBC void is real, lensing measurements should detect an underdensity in the matter distribution corresponding to the void. Some lensing studies have found evidence for such an underdensity, though the statistical significance is marginal. Lensing is a powerful technique, but is also challenging, requiring precise measurements of galaxy shapes and careful control of systematic errors. As lensing surveys improve in size and quality, they will provide increasingly strong tests of the void hypothesis. The convergence of evidence from multiple independent techniques is what ultimately builds confidence in a scientific result. No single observation is perfect, and every measurement has uncertainties and potential systematic errors. But if multiple different methods, each with their own limitations and biases, all point to the same conclusion, then that conclusion becomes robust. For the KBC void, the evidence is building but not yet overwhelming. Galaxy counts show an underdensity. Peculiar velocity measurements suggest outward flows. The Hubble tension could be explained by void effects. Lensing and kinematic Sunyaev-Zel'dovich observations provide hints, but not definitive confirmation. The integrated Sachs-Wolf effect is consistent with the presence of a large void. Taken together, these observations suggest that we do live in an underdense region, but the exact size, depth, and significance of that region remain subjects of active research. The coming decade, with new surveys and new data, will clarify the picture and determine whether the void is a major feature of our cosmic environment or a more subtle effect than current studies suggest. Beyond the specifics of the KBC void, the broader lesson is about the nature of cosmological measurement and the challenges of inferring global properties from a single vantage point. We are embedded observers, unable to step outside the universe and view it from an external perspective. Every observation we make is filtered through the structure and history of the cosmos between us and the objects we observe. Light is bent by gravity, redshifted by expansion, scattered by gas and dust, absorbed by intervening matter. The farther we look, the further back in time we see, and the more these effects accumulate. Nearby objects are seen as they are now, or at least as they were in the recent past, and their light carries information about local conditions. Distant objects are seen as they were billions of years ago, when a universe was younger and different, and their light carries information about cosmic history. Disentangling what is local from what is global, what is due to structure along the line of sight from what is intrinsic to the source, what is an effect of expansion from what is an effect of motion. These are the central challenges of cosmology, and they require both careful observation and sophisticated modeling. The models we use to interpret observations are built on physical laws: general relativity for gravity, thermodynamics for the behavior of gas, quantum mechanics for the formation of atoms and molecules, nuclear physics for the fusion reactions in stars. These laws are well tested in laboratories and in the solar system, and we assume that they hold throughout the universe, unchanged across billions of light years and billions of years. This assumption is not arbitrary. It is supported by the consistency of observations, by the fact that distant galaxies seem to obey the same physics as nearby ones, that the spectra of starlight from distant galaxies show the same atomic lines as starlight from the sun, that the cosmic microwave background fits the predictions of thermodynamics applied to the early universe. But the assumption is still an assumption, and there are corners of the universe where it has not been tested directly. The interiors of black holes, the moments immediately after the Big Bang, the nature of dark matter and dark energy, these are regimes where we extrapolate our physical laws beyond the domains where they have been verified, and we do so with caution and with the recognition that new physics might await. The KBC void does not require new physics. It can be understood within the framework of general relativity and the standard model of cosmology. But its existence reminds us that the universe is not uniform, that local conditions matter, and that our position in the cosmic web affects what we see and how we interpret it. The history of cosmology has been a history of expanding horizons, of discovering that the universe is larger, older, and more complex than previously imagined. In the early 20th century, the prevailing view was that the Milky Way was the entire universe, that the nebulous patches of light seen in telescopes were clouds of gas within our galaxy. Edwin Hubble's observations in the 1920s, using the newly completed 100-inch telescope on Mount Wilson, resolved individual stars in some of these nebulae and showed that they were galaxies in their own right, vast collections of stars far beyond the Milky Way. This discovery expanded the known universe by a factor of millions, transforming it from a single galaxy to an ocean of galaxies extending in all directions. Hubble's subsequent discovery of the redshift distance relation, the observation that distant galaxies are receding from us with velocities proportional to their distances, provided the first evidence for cosmic expansion and laid the foundation for the Big Bang model. Over the following decades, observations extended to greater and greater distances, revealing more galaxies, clusters of galaxies, superclusters, and eventually the large-scale structure of the cosmic web. The discovery of the cosmic microwave background in 1965 provided direct evidence that the universe had a hot, dense beginning, and precision measurements of this radiation have since provided the most detailed information about the early universe and the parameters of the cosmological model. Each of these discoveries has deepened our understanding, but also revealed new mysteries. The observation that galaxies rotate too fast to be held together by the gravity of their visible matter led to the dark matter hypothesis. The discovery that the expansion of the universe is accelerating led to the dark energy hypothesis. The Hubble tension and the discovery of large structures like the KBC void are the latest in this sequence of observations that challenge our models and push us to refine our understanding. It is possible that these new observations will be accommodated within the existing framework, that the void will be understood as a rare but allowed fluctuation, and the Hubble tension will be resolved by accounting for local effects, or by uncovering subtle systematic errors in the measurements. It is also possible that they point to something deeper, to new physics, or to a need to rethink the assumptions underlying the cosmological principle. Time and further observation will tell, but the process is a familiar one. Cosmology advances by confronting observations with theory, by testing models against data, by refining both as new information becomes available. It is a slow, iterative process, and it requires humility, the recognition that our understanding is always provisional, always subject to revision in light of new evidence. The philosophical implications of living in a void extend beyond the technical questions of measurement and bias. They touch on our sense of place in the cosmos, on the question of whether we are typical or atypical, central or peripheral, fortunate or cursed in our location. For much of human history, the prevailing view was that Earth occupied a central and significant position at the center of the universe, with the sun, moon, stars, and planets revolving around us. This view was challenged by Copernicus, who placed the sun at the center and Earth as just one of several planets orbiting it. The Copernican revolution was not just a change in astronomical models. It was a shift in worldview, a displacement of humanity from the center of the cosmos to a more humble position. Subsequent discoveries extended this displacement. The sun is not at the center of the Milky Way, but in the outskirts, about halfway from the center to the edge. The Milky Way is not at the center of the universe, but one of billions of galaxies scattered through space. There is no center to the universe, no privileged location, no place from which the view is fundamentally different or better. This is the essence of the cosmological principle, the idea that we are nowhere special, that the universe looks the same from every vantage point. But the discovery that we live in a large void suggests that while there may be no center, there are variations in environment, and our environment is somewhat unusual. We are not at the center of the void, which would itself be a special location, but we are somewhere inside it, and that fact affects our observations. Does this mean we are, in some sense, special after all? The answer depends on how you define special. If special means unique, the only place in the universe where certain conditions hold, then no, we are not special. There are presumably many other large voids in the universe, and many other galaxies within those voids, and observers in those galaxies would see similar effects. If special means rare, occupying an environment that is statistically unusual, then yes, we are somewhat special insofar as large voids are rarer than typical regions of the cosmic web. But rarity is a matter of degree, and the KBC void, while unusual, is not impossibly rare. It is a fluctuation within the expected range, and finding ourselves in one is not more surprising than winning a lottery with odds of, say, 1 in 100 or 1 in 1,000. Many galaxies will find themselves in such environments, and we happen to be one of them. The question of whether this rarity has any deeper significance, whether it tells us something about the conditions necessary for life or for intelligent observers, is speculative. It is possible that voids provide a more stable environment, with fewer galaxy collisions, less intense radiation from active galactic nuclei, or other advantages that make them more conducive to the development of complex life. It is also possible that voids are disadvantageous, with fewer nearby galaxies providing less opportunity for the exchange of material or signals. Without a larger sample of life-bearing planets, we cannot say which, if either, of these possibilities is correct. Another philosophical question raised by the void is the nature of explanation in cosmology. In most sciences, when we encounter an unusual observation, we seek an explanation in terms of causes, mechanisms, or laws that account for why the observation is the way it is. In cosmology, however, some observations may not have explanations beyond probability. The specific arrangement of galaxies, the sizes and shapes of particular structures, the fact that we happen to live in a certain galaxy in a certain void, these are contingent facts, accidents of cosmic history, shaped by the initial conditions of the universe and the subsequent evolution under physical laws, but not determined by any deeper principle. We can explain the statistical properties of large-scale structure, the distribution of void sizes and depths, the clustering of galaxies, because these are predictable consequences of the laws of gravity and the initial fluctuations. But we cannot explain why this particular void exists here, or why we are in it, beyond saying that it is one possible outcome allowed by the initial conditions and the laws, and that we happen to be in a universe where this outcome occurred. This distinction between statistical explanation and specific explanation is important in cosmology, and it can be unsatisfying. We're used to thinking that everything has a reason, a cause, but in a probabilistic universe, shaped by quantum fluctuations and chaotic dynamics, not everything does. Some things just are. The question of initial conditions is itself one of the deepest in cosmology. Where did the initial fluctuations come from? Why did the universe start in the particular state it did, with the particular density, temperature, and composition that led to the structures we see today? The leading answer is a theory called inflation, which posits that the very early universe underwent a brief period of exponential expansion, driven by a field called the inflaton, and that quantum fluctuations in this field were stretched to cosmic scales by the expansion, becoming the seeds of all structure. Inflation explains many features of a universe, including its flatness, its uniformity, and the spectrum of fluctuations observed in the cosmic microwave background. But inflation itself requires initial conditions, a universe in the right state to begin inflating, and it is not clear why the universe was in that state. Some versions of inflation suggest that inflation is eternal, that it continues forever in most of the universe, creating an infinite number of bubble universes with different properties, and that our universe is just one bubble among many. In this picture, the initial conditions of our universe are just the conditions that happen to hold in our bubble, and other bubbles have different conditions, leading to different structures, different laws, or even different numbers of dimensions. This is the multiverse hypothesis, and it pushes the question of explanation back another level, from why our universe has the properties it does to why the multiverse has the properties it does. At some point, the chain of explanation must end, either in a brute fact, a contingent initial condition that simply is, or in a principle that we have not yet discovered. These are questions that lie at the boundary of cosmology and philosophy, and they may not have empirical answers. We cannot observe other universes, if they exist, and we cannot rerun cosmic history to see what other outcomes might have occurred. We can only observe the one universe we inhabit, and we can ask what it tells us about the laws and initial conditions that shaped it. The KBC void is one piece of this puzzle, a structure that tells us about the growth of fluctuations, the dynamics of gravity, the effects of dark energy, and the challenges of measurement from an embedded perspective. It is not a key that unlocks all mysteries, but it is a reminder that the universe is rich, complex, and not fully understood, and that our position within it shapes not only what we see, but also the questions we ask and the answers we can find. As dark energy continues to dominate the expansion, the voids will grow, and the universe will become increasingly empty. The cosmic web, the filaments and walls that connect galaxies today, will thin and stretch, and eventually, they will be pulled apart by the accelerating expansion. Clusters of galaxies, held together by their own gravity, will survive as isolated structures, but they will be separated by ever larger voids, and the space between them will expand so fast that light cannot bridge the gap. The observable universe, defined as the region from which light has had time to reach us, will eventually stop growing and begin to shrink in content, if not in size. Galaxies beyond our local group will cross the cosmic horizon and disappear from view. The Hubble sphere, the distance at which the recession velocity equals the speed of light, will move inward, and as it does, the number of galaxies we can see will decrease. Billions of years from now, observers in the Milky Way, if any exist, will see a sky dominated by the Andromeda Galaxy, now merged with the Milky Way, and a handful of smaller galaxies in our local group, and they will see empty darkness beyond. They will not see the distant galaxies that we see today. They will not see the cosmic microwave background, which will have redshifted into invisibility. They will not have access to the evidence that the universe is expanding that it had a beginning, that it is much larger than their local region. This raises a haunting question. If we were born in that era, would we have developed cosmology as we know it? Would we have discovered the Big Bang, the expansion of the universe, the existence of dark energy? Or would we have concluded, based on the evidence available to us, that the universe is static, eternal, and consists only of our cluster? The answer is uncertain, but it is likely that our understanding would be fundamentally limited by the lack of observational evidence. We might infer from the dynamics of our cluster that the universe is governed by gravity, but we would have no direct evidence of expansion, no cosmic microwave background to study, no distant galaxies to measure. We might develop theories, but we cannot test them against the full range of phenomena that we can observe today. This thought experiment underscores the importance of the epoch in which we live. We are fortunate to exist at a time when a universe is old enough to have formed complex structures like stars and planets, but young enough that the evidence for its origin and evolution is still accessible. This is a narrow window in cosmic history, and it is one of the reasons why cosmology as a science has only developed in the last century, as our technology has advanced to the point where we can observe distant galaxies, measure their redshifts, detect the cosmic microwave background, and map large-scale structure. In earlier epochs, the universe was too hot and dense for stars to form. In later epochs, the evidence will be gone, erased by the expansion, and future observers will be left with a universe that looks very different from the one we see, a universe that may give them no hint of its true history. The KBC void is a microcosm of this larger process. Voids are regions where dark energy already dominates, where expansion is accelerating, where the evidence of surrounding structure is diminished by distance and redshift. By living in a void, we are, in a sense, living in a preview of the future, a region where the effects of dark energy are stronger than average, where galaxies are more isolated, where the density is lower and the expansion is faster. The void does not cut us off from the rest of the universe. We can still see distant galaxies, still measure the cosmic microwave background, still map large-scale structure. But it affects our measurements, introduces biases, makes the task of cosmology more challenging. And it reminds us that our ability to understand the universe is not guaranteed, not permanent, but contingent on our location, our epoch, and the availability of evidence. There is something unsettling about this realization, something that challenges the optimism inherent in the scientific enterprise. Science assumes that the universe is comprehensible, that through observation and reason, we can uncover the laws that govern it, that there are no barriers to knowledge except the limitations of our instruments and our intellects. But the case of living in a void and the case of future observers in an empty cosmos suggests that there are barriers, that our ability to understand the universe depends on being in the right place at the right time, and that some truths might be inaccessible to observers who live in the wrong era or the wrong location. This does not mean that science is futile, that we should give up the quest for understanding, but it does mean that we should approach that quest with humility, recognizing that our perspective is limited, that our knowledge is incomplete, and that there may be aspects of a universe that we cannot observe and therefore cannot know. This humility is appropriate not only for questions about the far future or distant regions of space, but also for questions about the present and the nearby. The Hubble tension, the question of whether we live in a void, the debate over the cosmological principle, these are questions about the here and now, about the universe we observe today, and yet we do not have definitive answers. We have models that fit most of the data most of the time, but there are discrepancies, tensions, anomalies, and it is not yet clear whether these are signs of new physics, of systematic errors in our measurements, or of biases introduced by our local environment. Resolving these questions will require more data, better instruments, more careful analysis, and perhaps new theoretical insights. It will take time, and it will require the collective effort of the cosmological community, observing, measuring, modeling, debating, refining. This is the process of science, and it is a process that never truly ends. Each answer raises new questions. Each observation reveals new puzzles, and the frontier of knowledge is always advancing, always receding, never quite within reach. In the meantime, we're left with a picture of the universe that is both awe-inspiring and deeply strange. We live in a cosmos that is vast beyond comprehension, populated by hundreds of billions of galaxies, each containing hundreds of billions of stars, each potentially surrounded by planets, some of which might harbor life. This cosmos is expanding, accelerating, driven by a mysterious dark energy that we do not understand. It is structured into a cosmic web of filaments, walls, and voids shaped by the gravity of dark matter that we cannot see. And we, inhabitants of a small rocky planet orbiting an ordinary star in the outskirts of an ordinary galaxy, find ourselves inside a large underdense region, a bubble of relative emptiness roughly 2 billion light-years across, falling through space with peculiar velocities imparted by the gravitational pull of distant structures. Our measurements of the expansion rate, of the matter density, of the age of the universe, are all filtered through this local environment, and we must account for it if we wish to infer the global properties of the cosmos. We are embedded observers, unable to step outside and view the universe objectively, and our perspective is shaped by where we are and when we are. This is not a comforting picture. It would be simpler, more satisfying, to believe that the universe is uniform, that our location does not matter, that the measurements we make here and now are representative of everywhere and every time. But the universe is not obligated to be simple or satisfying. It is what it is, indifferent to our preferences, shaped by laws and initial conditions that we did not choose and cannot change. Our task, as scientists and as sentient beings try to make sense of our existence, is to observe the universe as it is, to measure it as accurately as we can, to build models that fit the observations, and to remain open to the possibility that those models are incomplete, that there's more to learn, that the universe holds surprises. The KBC void is one such surprise, a structure that was predicted in broad terms by the theory of structure formation, but whose specific size and depth and our presence within it were not anticipated. It is a reminder that the universe is not a textbook, not a perfect realization of our models, but a messy, contingent, evolving system full of structure and variation, and that understanding it requires not just theory and mathematics, but also observation and measurement, and a willingness to let the data challenge our assumptions. The void is also a reminder of scale, of the vast distances that separate structures in the universe. 1 billion light-years is a distance almost impossible to grasp intuitively. Light, traveling at 300,000 kilometers per second, takes 1 billion years to cross the void. A spacecraft traveling at a significant fraction of the speed of light, a velocity far beyond anything we can achieve with current technology, would still take millions or billions of years to traverse it. For practical purposes, the void is uncrossable, a gulf that isolates us from the denser regions beyond. And yet, light does cross it. Photons from distant galaxies, emitted billions of years ago, travel through the void, through the emptiness, carrying information about those galaxies, about the conditions in the early universe, about the expansion and the structure and the history of the cosmos. These photons reach us, enter our telescopes, are detected by our instruments, and from them, we reconstruct the story of the universe. This is a remarkable feat, a testament to the power of observation and reason, and it is made possible by the fact that light travels, that information propagates, that the universe, for all its vastness and complexity, is not completely opaque or inaccessible. But the accessibility is not permanent. As the universe expands and dark energy accelerates the expansion, the distances between structures will grow, and the time it takes for light to travel those distances will increase. Eventually, for sufficiently distant structures, the expansion will be so fast that light will never reach us, no matter how long we wait. These structures will be beyond our cosmic horizon, causally disconnected, part of the universe, but not part of our observable universe. The horizon is not a fixed distance. It grows with time. As light has more time to travel, But in an accelerating universe, the growth slows and eventually stops, and in the far future, the horizon will begin to shrink as structures cross it and disappear. The void, by expanding faster than average, is hastening this process. Galaxies at the edge of the void are moving away from us faster than galaxies in denser regions, and they will cross the horizon sooner. The void is a preview of the horizon, a region where the effects of expansion are already strong, where the density is low and the distances are large, and where the cosmos is beginning to thin and empty. In this sense, the void is a place of transition, a boundary between the observable and the unobservable, between the accessible and the inaccessible, between the cosmos as we know it and the cosmos as it will become. It is not a sharp boundary, not a wall or a surface, but a gradient, a region where the properties of space and the behavior of expansion are shifting, where the balance between matter and dark energy is tilting, where the future is becoming visible in the present. By studying the void, we are studying this transition, learning how dark energy shapes structure, how expansion affects observation, how the universe is evolving toward a state of increasing isolation and emptiness. This is not a cheerful subject, not a story of progress or improvement, but a story of loss, of horizons shrinking, of knowledge becoming inaccessible, of civilizations, if they persist, being confined to smaller and smaller regions of space, cut off from the rest of the cosmos, alone in the darkness. It is a story that unfolds over trillions of years, far beyond the lifespan of any human, any civilization, perhaps even any galaxy, but it is the story that the observations tell, and it is the future that the laws of physics predict. And yet, even in this story of loss, there is a kind of beauty, a recognition of the impermanence and contingency of existence, of the fleeting nature of the window in which we find ourselves. We live in an era when the universe is knowable, when the evidence for its origin and evolution is still accessible, when the cosmic microwave background still glows in the sky, when distant galaxies are still within reach of our telescopes, when a large-scale structure is still being mapped, when cosmology is possible. This era will not last forever. It is a brief moment in cosmic history, a few billion years out of trillions, and we are fortunate to exist within it. This fortune is not a gift from the universe, which does not give gifts, but a consequence of the conditions necessary for complex life, which requires stars and planets and stable environments, and which therefore select for epochs and locations where such conditions can arise. But within the constraints of those conditions, we are lucky, and we should not take that luck for granted. The recognition of impermanence, of the limits of knowledge, of the contingency of our position in space and time, these are not reasons for despair, but for engagement, for the pursuit of understanding while it is still possible, for the asking of questions and the seeking of answers, knowing that the answers may be incomplete, that the questions may outlast us, that the universe is larger and older and stranger than we can fully comprehend. The KBC void is one small piece of this larger mystery, a structure that affects our measurements, challenges our assumptions, and reminds us that we are embedded in the cosmos, not outside it, not observing it from some privileged perspective, but part of it, shaped by it, limited by it. Our measurements are made from here, from now, from inside this underdense bubble, and they carry the imprint of that location. Accounting for that imprint, understanding how it biases our inferences, correcting for it, or at least acknowledging it. This is part of the work of cosmology, part of the challenge of being an embedded observer trying to understand the whole from a single point within it. The universe does not reveal itself easily. It does not present its properties in simple, unambiguous ways. It requires effort to observe, effort to measure, effort to interpret. It requires instruments that can detect faint signals, telescopes that can peer across billions of light years, detectors that can sense gravitational waves, satellites that can map the cosmic microwave background. It requires mathematics to model the observations, simulations to test the models, statistics to quantify uncertainties. It requires collaboration, the sharing of data and ideas across institutions and nations, the building of consensus through debate and evidence. And it requires humility, the recognition that our understanding is always provisional, that new observations may overturn old conclusions, that the universe is under no obligation to conform to our expectations. The KBC void is a case in point. It was not expected, not predicted in detail, not a central feature of the standard cosmological model. It emerged from observations, from careful surveys of galaxies, from the painstaking work of astronomers counting objects and measuring distances and comparing the results to models. It is an example of a universe surprising us, of reality being more complex than our theories, and of a need to remain flexible, to update our models when the data demand it. But updating models is not abandoning them. The Lambda CDM model remains the best description we have of the universe on large scales. It fits a vast array of observations, from the cosmic microwave background to the large-scale distribution of galaxies, to the abundances of light elements, to the accelerated expansion. The KBC void does not refute this model. It challenges some of its implications, particularly the assumption of perfect homogeneity on scales relevant to local measurements, but it does not contradict the model's core predictions. It is a fluctuation, a rare but a loud structure, and it can be accommodated within the framework if we are careful about how we interpret observations and account for local effects. The challenge is in the details, in the precise measurements, in the corrections for peculiar velocities and density variations, in the understanding of how local structure affects global inferences. This is where the frontier of cosmology lies, not in overthrowing the standard model, but in refining it, in understanding its predictions in greater detail, in testing it against increasingly precise observations, and in recognizing where it is approximate and where it is exact. In the end, the story of the KBC void is a story about measurement, about the difficulty of determining the properties of the universe from a single vantage point, about the ways in which local structure affects what we see, and about the philosophical implications of living in a cosmos that is not perfectly uniform. It is a story that begins with a simple observation, a deficit in the number of galaxies, and unfolds into questions about cosmic expansion, dark energy, the Hubble tension, the cosmological principle, the nature of observation, and the future of the universe. It is a story without a clear resolution, without definitive answers, because the data are still being collected, the models are still being refined, the debates are still ongoing. It is a story that will continue to evolve as new observations are made, as new surveys map larger volumes of space, as new instruments provide more precise measurements, and as cosmologists work to reconcile the tensions and anomalies that currently puzzle the field. And it is a story that reminds us of our place in the cosmos, not at the center, not on the periphery, but somewhere in the middle, inside a large underdense region, falling through space, carried by the expansion of the universe, observing the cosmos through the lens of our local environment, trying to piece together the global picture from the limited information that reaches us. We are embedded observers, and that embedding shapes everything we see, everything we measure, everything we infer. We cannot escape it, cannot step outside and view the universe objectively, but we can account for it, correct for it, understand it, and in doing so, we can approach a more accurate understanding of the cosmos as a whole. This is the work of cosmology, and it is work that continues, work that may never be complete, but work that is worth doing because it brings us closer to understanding the universe in which we find ourselves, this vast, strange, evolving cosmos, filled with structure and emptiness, with light and darkness, with matter and energy, expanding, accelerating, thinning, becoming ever more empty, ever more isolated, but still, for now, still observable, still knowable, still full of mysteries, waiting to be uncovered, waiting for observers to ask the right questions, to make the right measurements, to see what is there, not what we expect to be there, not what we want to be there, but what is there in all its complexity and indifference, in all its beauty and strangeness. We are here in this void, in this epoch, with these instruments, these theories, these observations, and we're trying to understand. We do not know if we will succeed, if the tensions will be resolved, if the anomalies will be explained, if the models will converge to a single consistent picture, or if new mysteries will emerge, new puzzles that require new physics, new ideas, new ways of thinking. We do not know what future observers, if they exist, will know or not know, what evidence will be available to them, what conclusions they will draw. We can only work with what we have, here and now, observing, measuring, thinking, questioning, building models, testing them, refining them, and remaining open to the possibility that the universe is more complex, more subtle, more strange than we currently imagine. The void is part of that strangeness, a reminder that the cosmos is not uniform, that location matters, that we're not standing on neutral ground, but inside a structure, a bubble, a hollow, falling through it, carried by it, and that our understanding is filtered through this fact, shaped by it, limited by it. This is what it means to live in the KBC void, to inhabit this underdense region, this thinning of space, this acceleration of expansion, this preview of the future, this place where matter is sparse and dark energy dominates, and galaxies move apart faster than the average, and where the measurements we make reflect not the universe as a whole, but the universe as it appears from here, from inside, from this particular contingent location in the vast structure of the cosmos. It is not a place of privilege, not a center, not a special point, but it is also not an average point, not perfectly representative, not neutral. It is a place, one of many, and we happen to be here, and that fact matters, and accounting for it is part of the challenge of understanding the universe, part of the work that remains to be done, part of the story that is still being written, by observations yet to be made, by questions yet to be answered, by a universe that continues to expand, to evolve, to reveal itself, slowly, reluctantly, in fragments and glimpses, to observers who are themselves part of it, embedded in it, shaped by it, trying to see beyond their own horizons, beyond their own epoch, beyond the limits of their position in space and time, reaching toward an understanding that may always remain just out of reach, asymptotic, approached but never fully attained, a goal that recedes as we advance, that grows more complex as we learn more, that opens new questions even as it answers old ones. And so we continue observing, measuring, thinking, knowing that the work is not finished, that the universe holds more than we have yet discovered, that the void is just one structure among many, that the Hubble tension is just one puzzle among many, that the cosmological principle is just one assumption among many, all of which must be tested, examined, questioned, refined, and that the answers, when they come, will not be final, not absolute, but provisional, contingent, subject to revision. Steps along a path that has no clear end, no ultimate destination, only the ongoing process of inquiry, of seeking, of trying to understand this cosmos in which we find ourselves, this universe of galaxies and voids, of expansion and acceleration, of matter and energy and space and time, vast and ancient and indifferent, beautiful and terrible and strange, knowable in part, but not in whole, accessible now, but not forever, a universe that is ours to observe and study and wonder at, for as long as we are here, for as long as the light still reaches us, for as long as the evidence remains, before the horizon's close, before the darkness deepens, before the void grows, before the universe becomes empty and silent and beyond the reach of knowledge, and we are left with only the memory of what we once could see, only the faint echo of the cosmos as it was, only the questions that remain, unanswered, suspended in the expanding emptiness, in the accelerating darkness, in the growing void, that surrounds us and encompasses us and defines the limits of what we can know.